Hello and welcome to all of you. This is Afroz from University of Brunei Darussalam. I'm an assistant professor of structural geology, and today I'll be talking about out of sequence faulting, not an exception but a rule, evidence from India Eurasia collision origin. As you can see from the title that this is an old problem, so I am regenerated this discussion, and the reason for that I'll be talking about more on that. Now, out of sequence faulting, as you can see that the name says that it is out of sequence, so there's something that is not in sequence, and that's the big question about what is not in sequence. So digging the information on this, it turns out that in the past, in fact, the two basic models that you can see from here is that I can see from here. Peach in 1907 says that the models are like this. You could go from B to C. What it says is that it says that A, like let's say that we had like the initial geometry of the sedimentary wedge, as you can represent from here, and these are the future thrust faults. Here's the foreland, here is the hinterland. So the question is that we've seen in the systematic that the faults, normally the reverse faults are the thrust faults, they migrate from hinterland towards the foreland. So in other words, the hinterland faults are older and the foreland faults towards the foreland are younger faults. So in the past they call this kind of sequence as break forward sequence. So in other words, the faults are breaking in the forward sequence, and is represented by B, where you can see that the fault here is the fault which started from somewhere here. Okay, first ramp, and then the second ramp is going to start. So 1, 2, 3 represents timing. This is the old one, and then followed by the new one, and followed the youngest one. So the youngest is towards the foreland. How it started as a ramp. So each one is basically a ramp, and they actually, there is a basal fault on which all of these faults basically, they root from that. Now so this is a back forward sequence, and in the present times we call this as in sequence faulting, right? And now the break back sequence means that you have a fault, for example here, the basement fault, and this basal fault ruptures the front first, and then it migrates towards the hinterland. So in other words, this is the hinterland younging of the faults. So this you can call as out of sequence because it is not in so-called sequence, right? So these are the two models that we proposed it, and as you can see here, the progression of active thrusting follows the hinterland to foreland sequence, popularly known as in-sequence thrusting, which is more. So the question is that what I'm going to raise now is that why would we call this out of sequence? What is out of sequence, in other words? And in other words, like, do we think that the faults do have a progression, that they actually migrate towards a particular, for example, in origins, they do migrate towards the foreland and they get younger? Does that mean that the other faults, which are in the hinterland side, they will not be active? And this is a big question, because if we call them in sequence, that means they do follow a sequence. Then we are making it formal that there is a sequence. But the question is, maybe there is not a sequence. So in other words, if you have a fault which is breaking the hinterland area, then you'll be asking questions about, okay, why is that hinterland area being where the fault is down there? So therefore, the question is that this widely accepted model that active deformation is progressing towards the foreland is known as in sequence. Any fault that does not follow sequence is called out of sequence. The question is whether it makes sense or not. So what we're going to do for the rest of the talk, I'll be taking you to some of the examples that we have from the northwestern Himalayas, and in fact you go to any origin and you will basically see the similar sequence, and we'll try to understand whether it makes sense or not. So here is our example from the active, this tectonics of this northwestern Himalaya. So what you're looking here for people who are not from this area, this is India, and India is colliding with Eurasia. As you know that in the past there was an ocean, the ocean is closed, now the two continents are in collision. The collision, what we have seen, the youngest fault that you see here is this red one, which is the main Himalayan frontal thrust. This is considered the most active fault in this area. In other words, the convergence from India, which is roughly 5 centimeters per year, is being taken up. Almost half of it has been taken up, more than 2 centimeters is taken up by this fault. The rest goes to the whole of the origin. So the question is that this fault, which is the main Himalayan frontal thrust, is the youngest fault. So in other words, in this sequence, we're talking about that this is the younger one right here, and this is the basically in sequence. It is initially. So with that thing in mind, it means that initially, one, somewhere here the fault was active where the suturing was happening. After that, it migrated here, 2, and then now it is in the 3, like just to make it aligned with the model that we have here. So if you have any fault which is getting activated in this area, that may not follow a sequence. So then that is an out of sequence faulting. But if that is correct, then we shouldn't have a lot of active faulting in the hinterland area, which is against the so-called in sequence faulting. Now, if you look at this carefully, what we have here also is that you got, for example, Karakoram fault, which is basically active fault. Again, it is on the other side of in fact, the interior of this origin. So let's concentrate mainly on this origin, this part of the origin, starting from the suture, which is at the left area, the main suture, and then we have the multiple sutures throughout this area, and then we have multiple faults, and then you got the frontal fault. So the question is that the frontal fault is mostly active. Would you expect it to have more activity compared to the other faults? If you ask me, I would say yes, why not? So it's just like this. You have two cars in collision, right? And you are, think about that, you are in a car, and it shouldn't happen. So I'm in the car. So the car is in the car got collided with other car, and there are other people on in the seats at the back. So when the collision happens, what is going to happen? The front is going to get more problem compared to the other side of this, like in the back, right? So the front is going to get more trouble compared to the back. The reason for that is because it is front, so it is taking more of the compression. So you have two plates converging. The main convergence will be taken by the front, and then the rest of that is going to take, but that the impact is going to take by the front. So the faults do exactly like that. They do take the main of the convergence part is taken by the front, but you do have the other parts also taking taking part into this convergence. But because they are most of the convergence, for example, out of the 5 there's like the centimeter of the convergence, if 2 is taken by the frontal fault, if you have multiple faults, how much convergence they will have? That means they will have low, right? So in other words, just like a food for the faults. Food for the fault is stress. So let's say that this 5 centimeters coming from here, the convergence. Out of that, half of the food is taken up by the frontal fault. So just half is distributed to so many people on the so many fault systems. So therefore, they will activate, but this gonna have their recurrence interval will be higher, whereas the recurrence interval of the front will be quicker, right? And that's what I think is happening. It's not like they're not active; they're active. I think it is not really possible to think that you have 2 plates in convergence and then the rest of the faults will not be activated. Will not be active. They are active, but they're taking less convergence. That's what I think. So and that's why we think that those faults are not active, but they take more time, but they can get activated. And we've seen that in Kashmir earthquake, when 2005 here, Muzaffarabad earthquake, more than 80,000 people died in that, unfortunately. And the reason for that was because, again, we were thinking about it as interior fault. It shouldn't be, we shouldn't have any problem with that, but that was not the case. So the question is that, and again, see the red dots that you see here, they are earthquakes. So all these earthquakes are also happening in the interior sites, which I will show you in a minute here. Okay, so here, for example, what I did, I took a very quick section of this and tried to see, okay, if you have seismicity, you can see that seismicity is everywhere. And look, the earthquakes, most of the depth of these earthquakes is less than 100. See, this is the 100 line. So they are less than 100 kilometers, the deeper. And what does that mean? That means it's a typical crustal seismicity. In fact, most of them are basically 50 kilometer, right? So it's a typical the crustal seismicity. But earthquakes are everywhere. It's not just like they are here only, they are everywhere. So again, telling you the story that earthquakes are constantly coming from those depths, and they are tectonic in origin. So the question is, why would you earthquakes come if those are so-called out of sequence faults? So there is nothing called out of sequence. As you can see from here, everything is in sequence. Do you understand? So the faults are, it's a systematic pattern of how faulting happens. There is basically no sequence. The fault, whatever fault gets more stressed, it's gonna break. It doesn't matter whether it's in the interior or in the frontal portion. That's what I think about. So if you look at these earthquakes that we have in the front, in this area, this is, some of people may think that, okay, these are tiny earthquakes, doesn't matter. But look at these. We have also big earthquakes happening in this region. And as you know, the Kashmir was 7.6, right? So we do have, like, the earthquakes are quite big, so they can be quite damaging. And again, to take an example from the Kashmir, and this is a basin, again, 100 kilometers away from the frontal faults, which is somewhere here. And what you're getting earthquakes inside Kashmir area, which may originate from the faults which are in the Kashmir area, or it may be on the frontal fault, which is ramping from the dam. But we have seen that there is actually active faulting in Kashmir area. Again, telling you the story that there are basically earthquakes which are originating from the faults in the hinterland area, not just at the front. And that's what I want to make a point. So here are some of the faults that we have mapped. So these are a sequence of faults. We have faults inside, and we have actually one of the faults which we recently mapped somewhere here, and it has a very clean active, it's an active fault, and exactly where the India-Eurasia suture zone is there located. So in other words, the suture zone is basically showing tectonically active features. The field work can actually tell us more story about it, but it actually is showing a very clear evidence of active faulting. So if you look at the earthquakes now, we want to know what type of earthquakes do you get. So normally the earthquakes that you have, or almost all types, they have normal, reverse, strikes. Basically all. So in the front you have reverse. In the interior faults you have basically normal and reverse strike slips. And then again, so as I said, that they are all types of earthquakes, okay? So it is not just like you're reading just one type of that. And here we made a model we published it recently, where we're actually expecting what type of earthquakes are expected in that particular area. For example, in this area, you're mainly expecting strike slips and normal. Reverse faults, there's a combination of strike slip and reverse faulting, strike slip, okay? I have less time, so we will try to finish it quickly. Okay, so this is like, we may think that this is just, in the northwestern Himalaya, but you can see that these are some of the major earthquakes, and they're all everywhere. Even, for example, in an area like Sunda Plate, so we have in Borneo, we have basically active faulting even happening in Borneo, which was considered, which is not really active. Okay, I'm a bit late, so that's fine. So just to conclude, the out-of-sequence faulting is presumed to be uncommon. However, our work shows that out-of-sequence faults are common in northwestern Himalaya and are related to the ongoing plate convergence between India and Eurasia. Therefore, we support the term regressive thrusts by Morley. So Morley used a term called regressive thrusts, and as the best explanation for out-of-sequence thrusts. Okay, thanks a lot, and I'm sorry for 38 seconds more. So if you have any question, I'll be happy to take questions. Thank you very much. And here is my email. Anyone wants to have any contact or anything, I'll be happy to deal with that. Okay, thank you, and stay safe.